The quality of our measurements can vary considerably, so the amount of acceptable error depends on the intended use of the measurement. In this video, we'll explore instrument calibration, error management, and quality standards. I'm Todd Horton for the Illinois Professional Land Surveyors Association. Every optical surveying instrument requires periodic calibration. Internal wear and tear caused by normal use and handling can slowly degrade instrument accuracy. Calibration includes carefully analyzing the instrument's accuracy and, if needed, adjusting it to restore degraded accuracy. Complex instruments like this total station may require calibration by a trained specialist. Common automatic levels can be calibrated by an experienced user. Collimation is the technical term for the adjusting of the line of sight in an optical device. To test this collimation of an automatic level, we commonly perform a peg test. The peg test is designed to determine whether the instrument line of sight is truly horizontal. If the level is out of calibration, then the line of sight can have either an upward or a downward slope leading to rod reading errors. To begin a peg test, we mark two stable points 200 to 300 feet apart and set up the instrument at the midpoint between them. In this configuration, we say that the back sight and foresight distances are balanced or equal. First, carefully read both rods and record readings R1 and R2. Because the distances are balanced and because the slope in the line of sight is identical for both readings, the error in reading R1 is equal to the error in R2. Therefore, these two errors, E1 and E2, cancel each other, and the true elevation difference is simply the difference in the two rod readings. For our example here, reading R1 is 5.43 feet, and reading R2 is 3.21 feet. So the true elevation difference is 2.22 feet. Next, we'll move the instrument to within 5 feet of one of the rods, making our sight distances highly imbalanced. Here we'll take readings R3 and R4, and once again the slope in the line of sight is identical for both readings. But now notice that error 3 and error 4 are now very different due to the imbalanced distances. In fact, because the distance to R3 is so short, error E3 rounds off to 0 feet. Here in our example, reading R3 is 4.72 feet and reading R4 is 6.97 feet. Now watch carefully. Reading R3 plus the elevation difference found from the first setup will give us a result called R4 ideal. R4 ideal is the theoretical reading we should get if the line of sight is truly horizontal. However, if the instrument requires adjustment, then R4 ideal will not equal reading R4, as you see here. When we subtract R4 ideal from reading R4, the difference is the vertical error in the instrument line of sight. To minimize this error, we adjust the crosshair of the instrument. Automatic levels typically contain at least one adjusting screw concealed under a cover that can raise or lower the crosshair to indicate the correct reading. This is a very tedious and delicate process. Experienced instrument operators can do this in the field. However, most people prefer to have this done by a trained specialist.
Whenever you use an optical level, your first question about that instrument should be, is it properly calibrated? Keep a permanent record of your calibration notes. If the instrument calibration is over 1 year old, it's overdue for another check. Some professionals calibrate their levels monthly to ensure quality measurements.
Use balanced distances to minimize the effects of possible calibration problems. Remember, when the distance to the backsight reading matches the distance to the foresight reading, the errors in each reading cancel each other. This gives the true elevation difference. This is nearly impossible to do in profile leveling, but it is especially desirable and achievable in benchmark leveling. When running a benchmark level circuit, do your best to keep each foresight distance balanced with its corresponding backsight distance. The lengths can change from one setup to the next, but try to keep the distances within each setup roughly the same as you can see here. Instrument calibration addresses the slope or tilt in the line of sight. Another type of tilt can also degrade our measurement accuracy, rod tilt. Our goal is to read the rod when it is truly vertical or plumb. But if it is tilted away from vertical, the line of sight no longer intersects the rod at the minimum distance above the measured point. When tilted, the rod shows a false reading that is numerically higher than the true vertical reading. So how can we ensure the rod is vertical? There are two common methods. First, this small device, often called a rod level, when held against the rod, uses a circular level vial to indicate when the rod is plumb. Second, if you don't have a rod level, you can rock the rod smoothly back and forth in the direction of the instrument. As the rod passes through the vertical position, the instrument operator will see the reading reach its minimum value momentarily. To ensure the rod is vertical relative to the instrument operator's left and right, stand behind the rod looking toward the instrument. Use your peripheral vision to search out visual clues to help you keep the rod plumb, left and right, as you rock it smoothly forward and back. Do your survey partner a favor. Grip the rod by its sides to prevent your fingers from obstructing the readings. These methods are designed to minimize errors, but it is impossible to completely eliminate measurement errors. So, how much error is acceptable? The size of acceptable error depends upon the intended use of the measurement. In previous videos, we indicated the overall accuracy of our level circuits using the circuit closure error. This is the difference between the known elevation and our computed elevation at the ending benchmark. To evaluate the quality of the work, we compare that circuit closure error to the allowable error. The allowable error depends on the horizontal length of the circuit from the starting benchmark through each turning point to the ending benchmark. For example, consider a closed loop circuit that is 3/4 mile long from beginning to end. The allowable error computation has just one input, circuit length. In this case, 3/4 or 0.75 mile. The result is plus or minus 0.043 feet. Since our circuit closure error is less than or equal to this allowable error, our level circuit is acceptable. However, if the closure error were to exceed the allowable error, the closure error would be unacceptable. The remedy then is to remeasure the circuit in part or in whole until the error source is discovered and corrected. This allowable error standard is one of the lower quality standards established by the FGCC, or Federal Geodetic Control Committee. Third order level enclosure, as we have seen here, is adequate for all agricultural and most construction and engineering applications.
To be successful in leveling requires careful error management. All measurements contain error, but by applying solid practices and anticipating a variety of error sources, you can perform leveling surveys with consistent accuracy and confidence. I'm Todd Horton for the Illinois Professional Land Surveyors Association.